What we're going to do in this video is derive a really interesting extension of Euler's formula, this time for the Quaternions, which is going to allow us to calculate e to a quaternion power. Euler's formula is among the most famous formulas in math, and what it allows us to do is calculate the exponentiation of a complex number. And what I mean by that is that if we have e as a base, and we raise e to some complex number power, Euler's formula allows us to give the complex number that results from that computation. And it says that e to the ix power is going to be cosine x as the new real part, plus I times sine x as the new imaginary part. And if you plug in the special case where x is equal to pi, we find that e to the I pi power is equal to minus 1. And if you move that to the left-hand side and you say that e to the I pi plus 1, you find that that's equal to 0, which is what we call Euler's identity. And to give another special case, if we plug in x equals 1 into this formula, the formula tells us that e to the I power is equal to cosine 1 as the new real part, which is 0.54, plus I times sine 1 as the new imaginary part, so 0.84i. And if we take yet another example, if we take numbers such as 2 plus I, which are some real number plus an imaginary part, as opposed to just a purely imaginary number here, if we take e to the 2 plus I, we can use our basic rules of exponentiation here. We can break this apart as e squared times e to the I, just like we would normally do if we have e to the a plus b power. We can break that apart as e to the a times e to the b power. And we find that e to the 2 plus I is going to be given by e squared times precisely what we found up above for e to the I. So we just take what we found up here and multiply by e squared, which will give us 3.99 plus 6.22i. And what we're going to do in this formula is derive an extension of Euler's formula for the Quaternions. And what that's going to allow us to do is calculate things like e to the I plus j plus k. And what we're also going to demonstrate, actually what I'm going to do is give you the tools to allow you to demonstrate an extension of Euler's identity for the Quaternions. And that's going to say that e to the I pi, e to the j pi, e to the k pi are all equal to minus 1, along with a couple others. E to the pi over square root of 2i plus pi over square root of 2j, that's also equal to minus 1. And lastly, e to the pi over root 3i plus pi over root 3j plus pi over root 3k is also equal to minus 1. Let me first review the Quaternions a little bit. In this video, we're going to think of a Quaternion as a four-dimensional object which can be written as a scalar part plus a three-dimensional vector part. That is, if I have a quaternion such as 1 plus I plus 2j plus 3k, I'm going to interpret this as 1 being the scalar part and the vector 1, 2, 3 as the 3 vector part. And this is normally how quaternions are interpreted anyway, so this is really nothing new. And in terms of notation, I could write it like this: 1 being inserted in that first place there, 1 being the scalar part, and this 3 vector, 1, 2, 3, being placed in the second component of this ordered pair. In general, I could write a quaternion like this. A quaternion Q can be written as the ordered pair where W is the scalar part and the vector V is going to be the vector part. In the above case, we had W is equal to 1 and the vector part was 1, 2, 3, which I wrote up here. And what we're going to need to know in this video is how to multiply quaternions. And if you don't already know, multiplying quaternions follows a very special rule, which is that if I have some quaternion, let's say Q1, which is given by W1, V1, and some other quaternion, Q2, which is given by W2, V2, the way in which I multiply Q1, Q2 is in the following way. The new scalar part is going to be given by W1 times W2 minus the dot product between V1 and V2. And the dot product, if you don't know that already, I encourage you to look that up. And the new vector part is going to be given by W1 times V2 plus W2 times V1 plus the cross product between V1 and V2 in that order. Because remember, the cross product, you can't commute them. It's V1 cross V2 if I'm multiplying Q1, Q2. So this is the rule we're going to need to know in this video. And in general, Quaternion multiplication is non-commutative. That is to say that Q1, Q2 is not the same as Q2 times Q1. Now, quaternion multiplication is a little bit complicated, but the only thing I'm really going to be doing in this video is I'm going to take powers of quaternions which have the form 0v. That is, quaternions which have 0 as a scalar part. I'm just going to be taking powers of them. That is, I'm going to calculate things like q squared, q cubed, q to the fourth, q to the fifth, and so on. So let's start calculating some powers of q. Now, q squared is going to be given by 0v multiplied by itself, 0v. And now we just follow the rule that I outlined in the last slide. The 0 being in the scalar part is going to simplify the formula. So I'm going to have 0 times 0, which is going to give me 0, minus the dot product of v with itself. So the new scalar part is going to be given by minus v dot v. And now the new vector part is going to be given by 0 times v and plus 0 times v plus the cross product of v with v. And if you don't know already, the cross product of a vector with itself is the 0 vector. So all in all, the new vector part is going to be the 0 vector. So this is a pretty simple formula for q squared. Just going to get negative v dot v for the new scalar part, and the vector part goes to 0. And what is negative v dot v? When I take the dot product of a vector with itself, that's simply the squared length of the vector. So negative v dot v is negative the length of v squared. And just to give you an example, let's say I have q, which is the quaternion 0 as the scalar part, and 1, 1, 1 as the vector part, which would also be written as just I plus j plus k. And let's square that. So we found up above that q squared is going to be the negative dot product of this vector, of the vector 1, 1, 1. The dot product of 1, 1, 1 with itself is going to be 3, so I just negate the 3 to get minus 3 as q squared. So you notice that we start with this quaternion, which is purely a vector, has 0 scalar part. When I square it, it's purely a scalar and no vector part. And now that's actually the toughest part of doing this calculation. From knowledge of q squared, we can now calculate the higher powers. Q cubed is just going to be q times q squared. And since I found that q squared is just a vector, I'm just going to take v and multiply it by negative the squared length of v. And that's going to be q cubed. And then q to the fourth, if q squared is equal to minus v, the length of v squared, then I just square that to get q to the fourth is equal to the length of v to the fourth power. I just square that value there. And in our example up above, I know what q squared was. That was minus 3. To find q cubed, I'm just going to take that minus 3 and multiply by v, that vector v. So I just take minus 3 times 1, 1, 1. And that's going to give me this vector here, which is minus 3, minus 3, minus 3. Then q to the fourth is just going to be the squared value of minus 3, which is 9. And what we have to observe here is that for even powers, like q squared, q to the fourth, we get only the scalar part. And for odd powers, such as q to the first, q cubed, then if you continue, it would be q to the fifth, and so on. It's some scalar times the original vector. And that's really the observation I want to make from these calculations here. And that's going to help in deriving Euler's formula for the quaternions. To derive our formula, we should first remember what we mean by exponentiation in general. What do we mean by e to the x? That is, when I plug this into my calculator, how does my calculator know what to do? So what we mean by e to the x is the following Taylor series, really. E to the x is given by 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial, and so on, where you have plus x to the n over n factorial. That's the definition of exponentiation. And if you're wondering why we started by calculating some powers of quaternions, this is why, in preparation for this calculation. So now that we know a few powers of q, let's plug in q into this formula. So now I'm going to have e to the q equals something over here on the right hand side. And what we're going to do first is assume that it has that form 0v, where the scalar part is 0. So we find that e to the q is equal to this formula here, just this formula with x being equal to q. And now from our knowledge of q squared, q to the third, q to the fourth, and so on, we can now do the substitution. Now q, we're assuming that it just has a special form where the scalar part is 0. Q is just equal to v, the vector v. We found that q squared was equal to negative the length squared of v, so I just make that substitution there. For q to the third, I find that it's this value, the negative squared length of v times v. All right, and then q to the fourth, I find that that's the length of v to the fourth power. Then if I continue, I'm going to find that q to the fifth is just that thing, the length of the fourth power times v. And I continue on, q to the sixth is going to be the negative length of v to the sixth power. And then hopefully you can see the pattern by this point. And then in the denominator, I just have n factorial. Here I have 0 factorial, here I have 1 factorial, here I have 2 factorial, 3, 4, and so on. Just making that substitution right into the power series for exponentiation. And now what we're going to do is we're going to make that observation that the even powers here, that is, this is like the 0th power here, this is the 2nd power, this is the 4th, the 6th power over here. These even powers are pure scalar parts. That is, 1 is a pure scalar, there's no vector part there. This thing right here is a pure scalar. This is a pure scalar here. And for all of the even powers. And furthermore, all the odd powers, this would be the first power here, this would be the third power here, the fifth, and so on. All of these are pure vector parts. That is, they're just some quantity, some coefficient times the vector v. For example, in the, let's say the third power here, third power because it's 3 factorial, it's that coefficient negative the squared length of v times v. These are the pure vector parts. So what we're going to do next is break these apart into scalar and vector parts. Up above, I've rewritten what we have so far for e to the q power. And first what we're going to do is have a look at the scalar part of this formula only. And just to remind you, this is going to be the even powers of q. So what I get when I isolate this is just this term, this term, this term, this one, and so on. And let's first observe the pattern here. So we see that this series is alternating. I have the plus here, minus, plus, minus, plus, and so on. And I see that these lengths of v are in every second power. I have the 0th power here, I have the 2nd, the 4th, the 6th, the 8th, and so on. So what does this power series remind you of? So this is what we're going to have to do now. We're going to have to find what function has this thing I have written here as its Taylor series. And hopefully that observation that we made about this thing being alternating, and it comes in every second power. I have the 0th, the 2nd, the 4th. That is to say, it skips all of the odd ones. I don't have a first power, I don't have a third or fifth or so on. And hopefully this reminds you of an even function, namely the cosine function. And if you have a look, if you remember the cosine function Taylor series looks like, it's going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. This is a cosine Taylor series in the case where x takes on the value length of v, which means that the scalar part is given by cosine of the length of v. And this is half the work already. So we found how to calculate the scalar part of the exponentiation of a quaternion already. And next we're going to have a look at the vector part of this formula. And again, up above, I've written out the complete series for e to the q. And now let's have a look at the vector part of this equation. That is, I'm going to have a look at this term, which is the first power of q. This is the third power here. I'm going to have a look at this, and so on. And I've written it in the following way. I've just factored out that v, so that this is going to be the coefficient that multiplies v. And as before, I'm going to want to observe this coefficient and find a nice compact way of representing this. That is, I want to know what function this Taylor series corresponds to. And now let's make a few observations. We see that it's, again, alternating. Here's plus, minus, plus, minus, plus. It comes every second degree. So this is in the length of v. We have the length of v to the 0 power here, to the 2nd power, to the 4th, to the 6th, to the 8th, the 10th. But in terms of powers, if we look at the denominators here, we'd really have a 1 factorial, 3 factorial, 5 factorial, 7 factorial. So it's really coming in only the odd powers. So from those two observations, we have an alternating Taylor series where only the odd powers are present. And just from that observation, you should be thinking of an odd function, just as before we were thinking of an even function. And combined with the fact that this is alternating, this resembles a sine function. If you remember what the Taylor series for a sine function is going to look like, it's going to look something like x minus x cubed. We normally have an x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. We'd have that alternating character there. So the only adjustment we really have to make here is that if the series that we see here were multiplied by an extra factor of the length of v, we would have the exact series for sine of the length of v. That is to say, if I took this coefficient series here and I multiplied the whole thing by the length of v, I would have the length of v minus the length of v cubed over 3 factorial plus length to the 5th power over 5, and that would be sine of the length of v exactly. Which means that what we're looking at is not sine of the length of v, it's actually sine of the length of v divided by v. So that's the value of the coefficient there, sine of the length of v divided by v, and then times the vector v. So this is the function that we're really looking at here in this Taylor series. So here we've just found what the vector part of the Quaternion exponential is. Let's now combine our results for the last two examinations of the Taylor series. So what we're saying is that e raised to a quaternion power that looks like ai plus bj plus ck. Remember, we're only able to deal with quaternions which have 0 scalar power for now. So the quaternion is going to have to look like this. This is going to be given by cosine of the length of v, where v is just this vector here, the entire thing, plus sine of the length of v divided by v, the length of v, times v itself. And remember, v is just this, so v, instead of writing the vector v there, I just plug in what we have up here. So this is really the formula here. And again, the length of v is going to be the square root of the sum of squares of the components of that vector, as it normally is. And now we have the formula, let's compute a few examples. So that means that e to the I plus j is going to be the vector v. That's given by cosine of the length of v. What is the length of v? It's going to be the square root of 1 plus 1, which is the square root of 2. So we find that this is equal to cosine of the square root of 2 as the new scalar part. And to find the new vector part, we have sine of the length of v, which is the square root of 2, divided by the length of v, which is again the square root of 2, times the vector itself, which is I plus j. And then you just distribute this to the I and to the j, and we find that the new quaternion that we get out of taking e to the I plus j is 0.156 plus 0.698i, and the same coefficient times j. And now let's take another example. Let's calculate e to the 3j plus 4k. So what's the length of this vector? I've selected the values pretty nicely. So we have the 3, 4, 5 thing going on there. So the length of this vector is going to be 5. So that means that the new scalar part of this quaternion exponential is going to be cosine of 5. Then the new vector part is going to be given by sine of 5 over 5 times the vector itself, which was 3j plus 4k. Then again, you just do the distribution here, and we find that the quaternion exponential of 3j plus 4k is equal to 0.284 minus 0.575j minus 0.767k. I'd like to now show you something very nice about the formula that we just found, and this will serve really as a sanity check for what we've just done. And what I claim is that this formula ought to reduce to Euler's formula when we try to calculate things like e to the I, e to the 2i, or even e to the j or e to the k. So let's do precisely that. Let's try calculating e to the ix with this formula. So I have e to the ix here, which means the vector in question is just x times I. X is that coefficient in front of I. The vector only has one component, just x, so the length of the vector is pretty simple. It's just x, which means when we plug it into the formula, we get cosine x plus sine of x divided by x times the vector itself, which is ix. And notice now that we get the cancellation of those x's there, and the formula does indeed reduce to Euler's formula. What this means is that what we just discovered, the formula that we just discovered for the Quaternion exponential, is really a generalization of Euler's formula, which is to say Euler's formula is a special case when the j and k coefficients go to 0. And now, to complete our discussion of this formula, remember how in our derivation we were making that assumption that the scalar part is 0. To be able to calculate the exponential of any quaternion, we have to take care of the case where it has non-zero scalar parts. Now I claim that when we go to calculate the quaternion exponential of something that has a scalar part, we can use a very similar trick as though we were trying to calculate something like e to the 2 plus I, where we wrote that as e squared times e to the I power. That is, we split up the scalar part with the imaginary part. Except now we're going to split up the scalar part with the vector part. Now I claim that if we have a quaternion that looks like this, a plus bi plus cj plus dk, we can split up the scalar part from the vector part in precisely the same way that we normally do with exponentiation. Now this is the claim. As an exercise, I encourage you to prove this, as this is not very difficult to show. You just work through the power series and you'll see that you can indeed split it up like this. You can split up the scalar part and the vector part. But I warn you not to split up the vector part within itself. You can't split up the bi from the cj, for example. And to take an example of what I'm talking about, let's suppose we want to calculate e to the 1 plus I plus j. I claim that we can split up that one scalar part from the I plus j vector part and write this as e to the first power times e to the I plus j. And since we know how to take care of something that looks like this already, e to the I plus j, this is simply going to be e times what we are already able to calculate. So if this holds, which it does hold, we now know how to calculate the Quaternion exponential for any quaternion. That is to say, if I have some arbitrary quaternion, let's say a plus bi plus cj plus dk, I can split up the scalar from the vector part, and the formula is going to be the following. It's going to be e to the a times this entire quantity, which again is going to be cosine of the length of v, and by v I mean bi plus cj plus dk. So it's going to be cosine of the length of v plus sine of the length of v divided by the length of v times the vector itself, which again is bi plus cj plus dk. And notice I've changed the letters a little bit here. But again, the length of v is going to be given by the sum of squares of the components, which were b, c, and d. It's going to be the square root of the sum of squares of the components. And this allows us to calculate the quaternion exponential of any quaternion. And notice in the special case, when c and d go to 0, I have something that looks like e to the a plus bi. And if you work through this formula here, you'll find that this is exactly what we have for Euler's formula. We have e to the a plus bi is given by e to the a power times cosine b plus I sine b. That'll wrap up this video. Just as a few practice problems, if you're really interested in this material. First, I ask you to show precisely what I claimed in the last slide, that I could break apart the scalar and the vector part like I normally do for exponentiation. Secondly, I ask you to convince yourself that the following statement is false. That is, that e to the I plus j is not the same as e to the I times e to the j. And make sure you do the calculation to convince yourself of that. And lastly, convince yourself of that Euler identity for the quaternions that I claimed in the first slide of this video, that the 5 quaternion exponentials I have listed here are all equal to -1.